There is a railway network between the collieries A, B, C, D and the coke ovens P, Q, R. The rail mileages between the collieries and coke ovens are given to us. The collieries can supply the following amounts in tons per month: A 3000, B 2000, C 8000 and D 3000. The requirements for coke ovens are: P is 2000 tons per month, Q 4000 tons per month, R 6000 tons per month. If the transportation cost is rupees 6 per ton mile, find out that distribution of coal from the collieries to the coke ovens which minimizes the total transportation cost. What is the minimum cost per month? So let's understand this example in more detail. So there are four collieries. Now what is a colliery first? So a colliery is a coal mine from where coal is obtained. So there are four of these: A, B, C and D. Let's say the first one is here. This is A. The second is here, B. Third is here, C. And the fourth one is here, D. And there are three coke ovens, P, Q, R. Now these coke ovens are not ovens which produce Coca-Cola. This coke refers to a byproduct produced when coal is heated under certain circumstances. And coke ovens are where coke is produced. Coke is considered to be one of the three fundamental materials for producing iron, which in turn is used to make steel. Now let's say these coke ovens are located here. So this is P, Q and R. Now there is a railway network between these collieries A, B, C, D and the coke ovens P, Q and R. So what this means is that we can transport coal from any of these collieries to any of these coke ovens. Now we have been given the mileage between these collieries and the coke ovens. So from A to P the distance is 10 miles. So distance is 10 miles. From A to Q the distance is 7 miles. And from A to R the distance is 28 miles. Similarly, from B to P the distance is 13 miles. From B to Q the distance is 8 miles. And from B to R distance is 27 miles. Similarly, we have been given the mileage from C and D to the coke ovens P, Q and R. Now the collieries can supply the following amounts in ton per month. So each of the collieries have a certain capacity, and A can produce 3000 tons of coal per month. So for A the supply capacity is 3000 tons per month. For B the supply capacity is 2000 tons per month. For C, the supply capacity is 8,000 tons per month. And for D, the supply capacity is 3,000 tons per month. Now, there is a certain demand or requirement for the coke ovens. P requires 2,000 tons per month. So the demand at P is 2,000 tons per month. Q requires 4,000 tons per month. And R requires 6,000 tons per month. Now, we have been given the transportation cost in rupees per ton mile. So what this means is the transportation cost is 6 rupees per ton mile. So for moving 1 ton of material per mile, it costs rupees 6. So now here we have been given the mileage, that is the distance in miles for moving the material from the collieries to the coke ovens. So we have to multiply these mileages with this cost per mile to get the cost of moving 1 ton of material from the collieries to the coke ovens. So let's say from A to P, the distance is 10 miles and the cost is rupees 6 per ton mile. So when we multiply this, the cost of moving the material from A to P will become 10 multiplied by 6 is equal to 60 rupees per ton. Let's understand a little bit more about the unit of measure, how it came to 60 rupees per ton. So the distance is 10 miles and the transportation cost is rupees 6 per ton mile. So when we multiply these two, we get 10 multiplied by 6 and then we get the unit of measure. So unit of measure will also get multiplied. So miles multiplied by rupees per ton mile. Now here what we do is we cancel these mile. So the unit of measure now becomes 10 multiplied by 6 rupees per ton. So this is how you derive the unit of measure based on the formula which you are using. So with this calculation, we'll know the cost of moving 1 ton of material from each of the collieries to each of the coke ovens. Now we have to find out the minimum cost of moving the material from the collieries to the coke ovens such that the supply and demand constraints are not violated. So let's try and do that using the transportation model. Now the first step in solving the transportation problem is to formulate the transportation table. In this step, we have to express the supply from origins, requirement at destination, and the cost of shipping from origins to destination in the form of a matrix. Now in our case, the origin are the collieries, the destination are the coke ovens, and because we have to minimize the total transportation cost, the cost of shipping is the cost of moving 1 unit of material from the collieries to the coke ovens. Now on the left hand side, I'll place the collieries because those are the supply origins. So the collieries are A, B, C, and D. And on the extreme right, I'll place their capacities. So the capacities are 3000, 2000, 8000, and 3000. And these capacities are in tons per month. Now on the top, we'll place the destination, which are the coke ovens. And we have P, Q, and R as our three coke ovens. And at the bottom, we'll place the demand at each of these three coke ovens. So this demand is also in tons per month. At P, the demand is for 2000 tons per month. At Q, it is 4000 tons per month, and R, it is 6000 tons per month. And in the middle, we'll place the transportation cost from each of the collieries to each of the coke ovens. Now again, this transportation cost is obtained by multiplying the mileage given in the example with the transportation cost per mile. So 60, 42, 168, 78, 48, 162, 84, 174, 96, 120, 138, 84. Now after we have created this transportation table, a check needs to be done to find out if the total supply and demand are equal. If yes, the problem is said to be balanced, and if not, a dummy origin or destination is added to balance the supply and demand. Because one of the basic assumptions in the transportation model is that the supply and demand should be equal. So let's total up the supply capacities. So 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 8 is 16, so 16,000. Now let's add up the demand. So 2 plus 4 is 6, 6 plus 6 is 12. So demand is 12,000 while supply is 16,000. So this is a case of an unbalanced transportation model. So to balance this, we'll have to add another source of demand with a demand of the differential between the supply and demand, that is 4000 tons per month. So let me modify this table to reflect that. So let's call this source of demand as S, and the demand is going to be 4000 because that is the difference between the supply and demand. Let me again note down the capacities. Now we have to determine a cost of moving these 4000 ton of coal from the collieries to this dummy source of demand. Now as such, there is no demand existing at the coke ovens. So the two options at the collieries is that either these 4000 tons is not even extracted, or it can be extracted and then kept in the inventory of the collieries and not be transported to any of the coke ovens. So in either of the cases, basically the transportation cost is going to be 0. So we'll put a transportation cost of 0 for moving these 4000 tons of coke from the collieries to this dummy destination. So now the total of supply and demand becomes 16,000 tons. So once we have completed the first step of formulating the transportation table, the next step is to establish the basic initial feasible solution. So let's use the Vogel's approximation method to establish this basic initial feasible solution. So this solution is going to be a feasible solution, and it may or may not be an optimal solution. So in Vogel's approximation method, first we have to find out the difference between the two minimum elements for each row and each column. So let's start row wise. So for the first row, the lowest is 0 and the next lowest is 42. So difference is 42 minus 0, which is 42. For the next row, 48 minus 0, 48. For the third row, 84 minus 0, 84. For the fourth row, 84 minus 0, it's 84. Now let's do the same for the columns. So for the first column, the lowest is 60 and the next lowest is 78. So 78 minus 60 is the penalty cost, which is 18. For the second column, lowest is 42 and the next lowest is 48. So 48 minus 42, which is 6. For the third column, 96 minus 84, which is 12. And for the fourth column, 0 minus 0, which is 0. Now we have to select the row or column which has the maximum penalty cost. So we have a tie between the two rows C and D. So we can choose any one of these. So let's choose the row C. Now for this row, we have to allocate the maximum possible to the square with the minimum cost. So that square is CS. So let's evaluate the supply and demand situation here. C has a supply capacity of 8,000 tons while S has a demand of 4,000 tons. So the maximum we can allocate here is 4,000. Now with this allocation, the capacity remaining at C becomes 4,000 while the demand remaining at S becomes 0. Now since the entire demand for S has been met, we'll cross off the remaining squares indicating that they are no longer required to be allocated. Now let's again determine the row and column differences. So for the first row, the lowest is 42 and the next lowest is 60. So the penalty cost is 60 minus 42, which is 18. For the second row, 78 minus 48, which is 30. For the third row, 96 minus 84, which is 12. For the fourth row, it is 120 minus 84, which is 36. Now for the first column, again 78 minus 60, which is 18. Second column, 48 minus 42, which is 6. Third column, 96 minus 84, which is 12. And we can skip the fourth column as it is completely allocated. Now again, let us select the row or column with the largest penalty cost. So D is that row which has the largest penalty cost. Now let's try to allocate the maximum to the square for this row which has the lowest cost. So the square is DR. Now let's evaluate the supply and demand situation. So D has a supply capacity of 3,000 tons while R has a demand of 6,000 tons. So the maximum we can allocate is 3,000. Now with this allocation, the supply remaining at D becomes 0 while the demand at R becomes 3,000 tons per month. Now since the entire supply at D has been completely exhausted, we'll cross off the remaining squares indicating that they are no longer available for allocation. Now let's redetermine the row and column differences. So for the first row, again the penalty cost is 60 minus 42, which is 18. For the second row, again 78 minus 48, which is 30. For the third row, 96 minus 84, which is 12. And we can skip the fourth row as it is completely allocated. For the first column, 78 minus 60, which is 18. Second column, 48 minus 42, which is 6. third column, the lowest is 96 and the next lowest is 162. So the difference is 162 minus 96, which is 66. And we can skip the fourth column as it is already allocated. Now the row or column with the largest penalty cost is the column R. So let's allocate the maximum to the square for column R with the lowest cost. So that square is CR. Now let's evaluate the supply and demand situation here. So C has a supply capacity of 4000 while R has a demand of 3000. So the maximum that can be allocated is 3000. So with this allocation, the entire demand at R is met and the supply remaining at C is now 1000 tons. Now since the entire demand at R has been met, so we'll cross off the remaining squares for R, indicating that they are no longer required to be allocated. Now let's redetermine the row and column differences. So for the first row, difference is still 18. Second row, 78 minus 48, which is 30. Third row, 174 minus 84, which is 90. We can skip the fourth row as it is completely allocated. Now for the columns, for the first column, the difference is still the same, 78 minus 60, which is 18. For the second column, 48 minus 42, which is 6. And the third column we can skip as it is completely allocated, and so is the fourth column. So now the largest penalty cost is for row C. So let's try to allocate to the square with the lowest cost, which is CP. So for C, the supply available is 1000 tons, while P has a demand of 2000 tons. So the maximum we can allocate here is 1000. So with this allocation, the supply available at C becomes 0, while the demand at P becomes 1000. Now since the entire supply has been exhausted at C, we'll cross off the remaining squares, indicating that they are no longer available for allocation. Now let's redetermine the row column differences. So for the first row, again 60 minus 42, which is 18. For the second row, 78 minus 48, which is 30. Third row is completely allocated, so we can skip this. Fourth row is also completely allocated, so we can skip this. For the first column, the same, 78 minus 60, 18. Second column, again the same, 48 minus 42, which is 6. Third column is completely allocated, so we can skip it, and so can we do for the fourth column. Now the largest penalty cost is 30 for row B. So let's allocate the maximum possible to square BQ because it has the lowest cost for this row now. So B has a supply capacity of 2000 while Q has a demand of 4000. So the maximum that can be allocated to this square is 2000. Now with this allocation, the entire supply at B has been exhausted, while the demand at Q becomes 2000. So let's cross off this box BP as the entire supply for B has been exhausted. Now we only have two boxes which are unallocated and not crossed off, which is AP and AQ. Let's first take the box which has the lowest cost of transportation, which is AQ, and try to allocate the maximum possible. So A has a supply capacity of 3000 while Q has a demand of 2000. So the maximum we can allocate here is 2000. So with this, the entire demand at Q has been met, while the supply capacity remaining at A is 1000. Now for the last square AP, the supply available at A is 1000 while The demand at P is also 1000, so we can allocate 1000. So now the entire demand at P has been met, and also the entire supply capacity at A has been exhausted. So this is the basic initial feasible solution, and it may or may not be the optimal solution. What that means is that this allocation will work for transporting the material from these collieries to the coke ovens, and will definitely not violate the supply and demand constraints. However, the cost of transportation may or may not be the lowest. So before we proceed with the optimality test, let's calculate the total cost of transportation that we have achieved using the Vogel's approximation method for this problem. So the total cost is equal to the units transported multiplied by the cost per unit. So 1000 multiplied by 60 plus 2000 multiplied by 42 plus 2000 multiplied by 48 plus 1000 multiplied by 84 plus 3000 multiplied by 96 plus 4000 multiplied by 0 plus 3000 multiplied by 84. So let me pull my calculator here. So 1000 multiplied by 60 plus 2000 multiplied by 42 plus 2000 multiplied by 48 plus 1000 multiplied by 84 plus 3000 multiplied by 96 plus 4000 multiplied by 0 plus 3000 multiplied by 84. So the total cost is 864,000 rupees. Now we have to find out if this solution is the optimal solution or not, and we can find that out by doing an optimality test. However, first we have to find out if this solution is acceptable to proceed with the optimality test. Now there are two conditions for checking for acceptability. The first one is that the number of allocations should be equal to m plus n minus 1, where m is the number of rows, n is the number of columns. So here we have 4 rows and 4 columns. So 4 plus 4, 8, minus 1 is 7. And this should be equal to the number of allocations. So let's count the number of allocations that we have. 1, 2, 3, 4, 5, 6, and 7. So the number of allocations is equal to m plus n minus 1. So the first condition is met. The second condition is that all the allocations should be in independent position, which means that it is impossible to travel from any allocation back to itself by a series of horizontal and vertical jumps from one occupied cell to another without a direct reversal of the route. So let's take the example of AQ and let's try to form a closed loop for this square. So from here we can go to AP and then to CP and then to CR, but from here there is no way we can come back to AQ using horizontal and vertical lines. So this means that we can't create the closed path for AQ, which means that this is in independent position. Similarly, if you evaluate all the other allocations, you will find that all of the allocations are in independent positions, which means that the second condition is also passed. So now we can proceed with the optimality test. So let's use the modified distribution method to perform the optimality test. Now the first step in the modified distribution method is to set up a cost matrix containing the unit cost associated with the cells for which allocations have been made. So here what I've done is I've created the cost matrix and I have noted down the unit cost for the stone squares or the squares which have an allocation. So for example, AP has an allocation, so I've noted the unit cost, which is 60. AQ has an allocation, so I've noted the unit cost of 42. AR does not have any allocation, so I have not noted the unit cost here, and so on. Now the next step is to assign the variable UI to each of the rows and VJ to each of the columns. So U1, U2, U3, U4, and this becomes V1, V2, V3, and V4. The next step is to compute the values of U and V for the stone squares such that UI plus VJ is equal to CIJ. CIJ is the value of unit cost for the stone squares. So for the first stone square, U1 plus V1 is 60. Second one, U1 plus V2 is 42. Third, U2 plus V2 is 48. Fourth, U3 plus V1 is 84. Then U3 plus V3 is 96. Then U3 plus V4 is 0. And the last one, U4 plus V3 is 84. Now since there are m plus n, that is 4 plus 4, 8 variables, however, the number of allocations are m plus n minus 1. We can assume one variable to be 0 arbitrarily. So let's assume V1 as 0. And with this, let's try to find out the remaining value of the variables U, I, and Vj's. So V1 is 0, so U1 becomes 60. So U1 is 60 and V1 is 0. Now U1 is 60, so V2 becomes 42 minus 60. So U1 is 60 and V2 is 42 minus 60, which is minus 18. Now V2 is minus 18, so U2 becomes 48 plus 18, which is 66. So U2 is 66 and V2 is minus 18. Now V1 is 0, so U3 is 84. Now U3 is 84, so V3 becomes 96 minus 84, which is 12. Now again U3 is 84, so V4 becomes minus 84. Now the last equation, V3 is 12, so U4 becomes 84 minus 12, which is 72. So U4 is equal to 72 and V3 is equal to 12. So using these values of UI and VJs, now let's calculate the net cost change value for the water squares. So let's see how we can do that. So in this matrix, what I've done is I have also noted the unit cost of transportation for the water squares, but I have noted them in red color. So the ones in red color are the ones for the water squares, while the ones in the black color are for the stone squares. Now let me also note down the values of UI and VJ that we had achieved in the previous step. So U1 is 60, U2 is 66, U3 is 84, and U4 is 72. V1 is 0, V2 is minus 18, V3 is 12 and V4 is minus 84. Now in this step we have to calculate the net cost change for each of the water squares. So what this means is that we are trying to figure out that if we make an allocation to any of these water squares, then what will be the impact on the total cost? Will it go down or will it go up? So this net cost change is found out by calculating Cij minus Ui plus Vj for each of the water squares. So let me create a table for ease of calculation. Now the first water square is AR. So for AR, Cij is 168, Ui is 60, and Vj is 12. So 60 plus 12 is 72, and 168 minus 72 is 96. Now the next water square is AS. Cij is 0, minus Ui is 60, and Vj is minus 84. So 60 minus 84 is minus 24, and then there is a negative sign outside, so minus minus will become plus. So this value is 24. The next water square is BP. Cij is 78, Ui is 66, and Vj is 0. So 78 minus 66, the value is 12. The next water square is BR. The value of Cij is 162, minus Ui is 66, and Vj is 12. So 162 minus 78, the value is 84. The next water square is BS. Cij is 0, Ui is 66, and Vj is minus 84. So 66 minus 84 is minus 18, and there is a negative sign outside, so minus minus plus becomes 18. The next water square is CQ. Cij is 174, Ui is 84, and Vj is minus 18. So 84 minus 18 is 66, and 174 minus 66 is 108. The next water square is DP. Cij is 120, Ui is 72, and Vj is 0. So 120 minus 72, the answer is 48. The next water square is DQ. Cij is 138, Ui is 72, and Vj is minus 18. Now 72 minus 18 is 54, and 138 minus 54 is 84. And the last water square is DS. Cij is 0, Ui is 72, Vj is minus 84. Now 72 minus 84 is minus 12, and there is a negative sign outside, so minus minus plus, the value is 12. So after we have found out the net cost change values for all the water squares, we have to evaluate the solution for optimality by reviewing the sign of the net cost change values. So if all the values are positive, which is true in our case, then the optimal solution has been reached. So the basic initial feasible solution that we had achieved using the Vogel's approximation method is the optimal solution as well. And the total transportation cost was 864,000 rupees. So in this example, we didn't have to iterate towards optimality, as the basic initial feasible solution itself turned out to be the optimal solution.